Hello everyone and welcome to 11th lecture of digital elevation models and applications. And in this model, in this lecture and after this, we will be discussing various derivatives of digital elevation models. As also mentioned earlier, that digital elevation model is a storehouse of information. We can retrieve many types of informations from it. And some people also put as a terrain analysis when we drive the terrain parameters, especially it is meant only for that. So, it is also called terrain analysis, that is the derivations of terrain parameters starting from slope, aspect and drainage network, watershed boundary and topographic position index and many other things. So, we will be seeing one by one all these things and how these can be applied, how these can be used for various engineering and other applications, that too we will be seeing this. So, terrain analysis is basically the analysis and interpretation of topographic features employing DEMs through GIS. So, we have to have a GIS platform on which we can derive lot of terrain parameters using various digital elevation models as per our requirements. Second thing is that such features as mentioned, that slope, aspect, view set, elevations, contour lines, flow, upslope flow lines, downslope flow line and various other parameters can be derived from digital elevation models. As the availability of digital elevation models or global digital elevation models from various sources are becoming possible or available, more applications and more derivatives people are developing through on GIS platform using these DEMs. And basically here what we try or what we intend to build mathematical abstractions of surface terrain in order to delineate or stratify landscape. And the purpose here is that because that for every derivative of digital elevation model, of course, there is a mathematics behind it. And as more requirements of processing is there, so more development in the mathematical domain is also taking place, how to exploit digital elevation models to this maximum. So, people are employing not only for terrain parameters, but for other parameters, even for landform identification, depending on the spatial resolution and requirement. So, basically if we start from say slope point of view, then the area of a sloping pixel is not the same size as one that lies flat, and sloped pixels occupies more area than a flat one, as we will see very soon a diagram through which we can understand. So, that basically here what we are trying to discuss here, that if it is a flat terrain, then the area is going to be less for a one cell, whereas if it is a sloping cell or a undulating terrain and there is a sloping cell, then the area of that sloping cell is going to be more. So, it is planimetric area versus sloping area that we are going to discuss in detail. So, the planimetric to surface area ratio we can exploit, and that becomes an index of topographic roughness, and which can be used for various purposes, especially for habitat assessments, erosional studies, land use studies and even to geomorphology. And this index is largely independent of scale. So, it does not matter that what is the resolution or what is the scale of a digital elevation model. And common sense, as we know, that suggests that if we walk up and down in steep terrain, we will walk more than in planimetric length of your path. So, if we have to because the length also increases in case of a sloping terrain, whereas if we have to walk on a flatted terrain, then the length is not that much as compared to the sloping length. And while we know that this fact of thousands of years, surface area and length calculation were practically impossible to apply to the topographic maps or paper maps which we were using. But now employing the digital elevation models, which is a two-dimensional matrix, we can calculate these planimetric area, we can calculate the surface area and sloping areas and also indices for surface roughness. So DM with GIS can handle all these such calculations. In a vector system, that when we are having contour lines and other things, these calculations to some extent are also possible. But in a grid based system, the planimetry area is calculated by multiplying the number of cells defining a map feature times the area of individual cell. And for example, if a forest cover type occupies say for 500 cells with a spatial resolution of 1 hectare each, the total planimetric area for cover type would be 500 hectares. 500 multiplied by 1 hectare per cell. And this is what I wanted to show to you, that if it's a flat terrain, like for example Indo-Gangetic plain of northern India, then this is the scenario you might be facing, that your cell is completely flat here, and this will become our horizontal plane or planimetric area. Whereas if a cell is representing a sloping terrain like in part of Himalaya, then it will have more area. So the planimetry area is always less than the tilted plane or tilted area. So with the surface area increases with increasing inclination. This we can conclude very easily. But in case of topographic maps as shown below, where we use the just simple contours, such calculations to high accuracy is not possible. So this actual surface area of each grid cell is dependent on its inclination, that is basically the slope, and the surface area increases as grid cell tilted from a horizontal reference plane, as in this case we can see this is the horizontal reference plane in the bottom, and reference plane to its three-dimensional, and this is the three-dimensional representation of the same terrain in through a digital elevation model. So this is the major discussion in this topic, that how we can calculate planimetric area and sloping area and indices, and what are the intricacies while doing all this thing. So if we take the top left figure here, this is the planimetry area when your cell of a digital elevation model is representing a flat terrain. But when it is representing a tilted terrain, then this becomes a sort of rectangular in that sense. Though if we project on a horizontal plane as shown in the bottom, then it will remain of course a square, because a square is the unit of a digital elevation model. But in case of a tilted one, it becomes a sort of rectangular, and then it will have more area than a square. And this is orthogonal surface area, and this is non-orthogonal surface area, where it is not having a 45-degree with this length. So when you are having a parallelogram here, and this becomes a non-orthogonal area. So in non-orthogonal surface area forms a parallelogram and is calculated in the same manner as orthogonal surface. So it is not necessary that in digital elevation models the slopes will be only calculated for north-south sloping. They may be in any direction. So all kinds of in all directions slopes can be calculated, or the area of those sloping surfaces can also be calculated. So surface area can be calculated by dividing the planimetric area by the cosine of the slope angle. And for example, a grid location with a 20% slope has a surface area of 1.0198 hectares based on solving the following sequence of equations, and that the 10 slope angle equal to 20% slope divided by 100 equal to 0.20 slope ratio. And similarly, slope angle can also be calculated as mentioned in this equation. So, surface area or the factor surface area factor is also can be calculated in a similar way using these equations, and surface area first surface area factor, now surface area, that too can be calculated. So, that is why when we say this, that when a grid location with a 20% slope has a surface area of this is how we reach here with this 1.019803 hectares. So, this is how the area of a sloping surface can be calculated. And this table below basically what identifies the surface area calculated for 1 hectare grading resolution under several terrain slope conditions. So, here when as slope increases, how the area also increases. As you can see, when you are having a flat terrain, the surface area is going to be perfect 1 hectare, but say if it is a slope percent is a 80%, then it is going to be 1.28, and then we go for 200%, it increases, and likewise. So, that the column here, what the surface area factor, this one is independent of grading resolution, that it is independent from spatial resolution of digital elevation model, and the driving surface area for a cell on a 5 hectare resolution map simply changes the last step in the 20% slope example here. And in this one only it will change as per the resolution, but the result would remain same. This is we can see this planimetric area versus surface area or area of a sloping surface through these two figures. Left one is simple digital elevation model, and here the z axis has not been given except gray value. It has not been given any height scale, and therefore what you are seeing only in the shades of gray. The lighter color toned cells are representing the higher grounds, whereas the darker one are representing the lower grounds. So, here like for example, for this total digital elevation area coverage, this planimetric area is going to be this much, because multiply by the number of cells multiply by the spatial resolution, whereas since it is the surface area and this is the same terrain, same digital elevation model has been represented through a shadow relief model, and where the z axis has been given basically it has been used as a z axis, and therefore you are having now sloping areas as well. And when we are having something like this, then the surface area for all these slopes which are being seen here, it is going to be more area than a simple planimetric area, and this is what it is depicted here, that here it is 8100 square meter and here is 13,366 square meter. So, this is definitely will have the more surface area. If someone calculates even for a hilly terrain, if someone calculates the area or surface area as planimetry for the flat terrain, then he is going to make lot of wrong interpretations or wrong calculations for the area which is available in a hilly terrain. So, this has to be kept always in mind, because all terrain, or rather most of the terrain, are not flat. There are some undulations even in endoganglic planes. So, therefore, this care has to be taken while calculating the surface area of a terrain or through a digital elevation model. Another thing which also plays very important role is the surface curvature. How these sloping surfaces are having curved, whether upslope, downslope, or across slope or along slope, all these or in combination. So, all these will also influence the area and therefore other processes, for example erosional processes, depositional processes, and maybe in case of landslide they are going to behave completely differently. So we have to also see these parameters. So surface curvature at a point is the curvature of a line formed by intersection of surface with plane and a specific orientation passing through this point. And this the value of curvature is reciprocal of radius of curve. The larger the radius, the smaller the curvature value. A gentle curve has a small curvature and a tight curve has a large curvature value, and this we will see also through diagrams. And this units of curvature are in radians, and per linear unit, that is the unit here is the spatial reference of the raster or our digital elevation model. We may be having digital elevation models, that is the horizontal scale and reference system in meters in case of UTM, or may be having in latitude longitude. So depending on that unit we will have the total curvature units. And now these curvatures can also be, there are various types of curvature. So we will take one by one. The first and the simple one is the plan curvature. That means the curvature which we see from that. So the plan curvature is measured in a horizontal plane, and that is the curvature in a horizontal plane. As we can see, there can be two types of plan curvature: negative, that is concave, and positive, that is the convex. Now the curvature of the slope and concave and convex, that means positive and negative and positive, will behave differently in different natural processes, erosional processes or in other cases. So it can also, this plan curvature can also be described as the curvature by the hypothetical contour line that passes through a specific cell. And this plan curvature is positive for cells with concave contours and negative for cells with convex contours. Here, instead of discrete lines like contours in a digital elevation models, we are going to have cells or a continuous grid, but does not matter, and the concept by it will remain same. So plan curvature can be used to differentiate between ridges and valleys, as we are seeing here also. And when you are having positive curvature, positive plan curvature, then this is a representation of a ridge kind of situation in this particular schematic. And when you are having negative, that is concave, then these are the indications of valleys, as you can see here. Now this plan form of plan curvature, commonly called plan curvature, is perpendicular to the direction of maximum slope. As we have seen here, that this is perpendicular to the direction of slope. Always we measure in that way. And then the plan curvature relates to the convergence and divergence of flow across a surface, because these curvature values we can use to estimate erosional processes in a hilly terrain, and therefore the convergence and divergence of flow becomes very important also. So this is like example here, that in example A, we are having positive plan curvature, that is indicating a surface is laterally convex at that particular cell here, and whereas a negative plan B indicates here that the surface is laterally concave at the cell. So laterally it is concave here, and a value of 0 indicates the surface is linear, that is the surface is flat. In natural surfaces are generally not like that. There may be some curvatures, and that has to be for better estimations of erosional processes or flow processes or any other engineering applications. We need to calculate all these parameters. Now one was the plan curvature. Now another one is the profile curvature. What is profile curvature? Is that curvature of the surface in the direction of a steepest slope is the vertical plan of the flow line. So here, like here we can see these are the direction of steepest slopes which are shown here. So this red one are showing the negative or convex profile curvatures, as we can see here. And whereas the positive or these concave, here green, are showing positive profile curvature. So, this is profile curvature is the curvature of the surface in the direction of steepest slope, and that is in vertical plane. So, plan curvature is measured in horizontal plane, whereas profile curvature, as name implies, measured in a vertical plane. And profile curvature affects the flow velocity of water draining in the surface and influences erosional and depositional processes. And in location with the convex, that is negative profile curvature, the erosion will prevail. In case of like this, when you are having a negative or convex profile curvature, you expect more erosion, and in case of positive, that is concave, there might be possibility of deposition or less erosion. So, that is why the calculation of these curvatures are important. Further, that the profile curvature is parallel to slope and indicates the direction of maximum slope, and because we are seeing or measuring in a vertical plane, and it affects the acceleration or deceleration of flow across the surface. In case of plan curvature, we were thinking of flow divergent and convergent flow. Here what we are seeing the acceleration or deceleration, because we are measuring in vertical plane, and it affects the velocity of your flow. So, a negative value in case of a profile curvature indicates the surface is upward convex, as in case of scenario A at the cell, and the flow will be deaccelerated because it has to pass through a curved surface up slope, upwardly convex slope. Whereas in case of profile curvature, like in B, when you are having upwardly concave at the cell, the flow will be accelerated. Here we will have more flow, here we are going to be a deaccelerated slope. And in case of flat, it is when the value of 0 indicates the surface is linear. So, in case of our plan curvature, the same scenario was there, that a value of 0 indicates surface is linear. So, when you do not have any curvature, then in both the cases, in case of plan curvature as well as in profile curvature, we will have this value, curvature value 0. Now, there is another curvature which is called in different literatures, in different softwares, different words have been used, like for example general curvature, maybe total curvature, or a standard curvature. That is basically combining both. So, general curvature, that is also called the total curvature, is the curvature of the surface itself, not the curvature of a line formed by the intersection of the surface with a plane. So, like in plan curvature, we thought the line is going or passing through a horizontal plane or cutting through a horizontal plane, whereas in case of profile curvature, because we measure in vertical plane, so we have been thinking about the line. Here now it is the total one. So, instead of line, the complete one is here, like the example given here, that in case of positive, the green one is shown here, and these are the all ridges part which you are seeing the total curvature, and in case of negative, which is convex, and what we concave, sorry, and what we are seeing is all if these are the ridges, then these are the valleys part. So, general curvature can be positive or convex, indicating peaks like here in the green colored one, and negative or concave indicating valleys, and of course 0 indicating flat surface or a saddle. So, this is how we see these curvatures. Further, this standard curvature combines both the profile curvature as well as the plan curvature, and profile curvature affects the acceleration and deceleration of flow and therefore influences erosion and deposition, whereas plan curvature influences convergent and divergent of flow, and accordingly it will affect ultimately the erosional processes and depositional process as well. So, considering both in plan and profile curvatures together allows us to understand more accurately the flow across a slope, because normally the slopes are not in a plane form. They are either you are having concave or convex, and they behave completely differently for different natural processes like erosion or deposition. So, in this the diagram which we are going to have on the right side, there are different these things are shown, that the columns shown here the plan forms curvature and the rows show the profile curvature. So, in this way what we are seeing the plan form curvature, and in row direction we are seeing the profile curve. And this plan form are positive here, like here they are you are seeing positive and negative, and also 0 are in the last. So, that is in the here also. So, profile curves are negative, positive or 0 going to the top to the bottom. So, all kinds of scenarios have been incorporated in this particular diagram. Now land classification or terrain classification is also possible based upon a combination of both these curvatures, horizontal or vertical curvature or plan curvature or profile curvature, as shown here, that when convergent things are there, then it is associated with accelerating of flow. When you are having divergent, these lines indicates whether they are converting or diverging, and they are basically showing the shapes of our cells which will be representing the sloping surfaces. So, when you are having accelerating such scenario, you will in this the here in the bottom left we are having the convergent deaccelerating scenario. This is also this is just opposite, divergent also here, but deaccelerating. So, in the top two cases we are having accelerating scenario, but convergent and divergent flow is possible. Here convergent, divergent both are representing the deacceleration scenario. So, likewise these can be exploited to understand a terrain in a much better manner for erosional and depositional processes. In geomorphology, classification of landforms on the basis of plan and profile curvature is also possible, as shown here, that on the rows we are having profile curvature, here we are having plan curvature, and then we are having the convex scenario. So, in both the cases it is convex, and this is one. Then you are having in the both the cases it is concave. These are the two extreme members, and then you can have in between the other. So, the slopes can be classified like in case of scenario 1, where both plan and profile are showing the convexity of the slope, then we say nose slope. When we are having in case of like this scenario 2, where profile is straight and plan is also straight, then we say side slope. When we are having scenario 3, when profile is concave, plan is concave, then we say head slope. And there are other mixed scenario, like in profile curvature you are having convex, and in plan you are having straight, then we say shoulder, and then negative in case of fifth one, whereas a profile concave and plan straight, then we get negative scenario. So, these basically are indicating that how we can classify different types of slopes based on the curvature values. How exactly it is calculated in GIS using a digital elevation model, and this is what it is depicted here, that on the left side we are having a digital elevation model, and the values are shown. MV stands for no data, basically no value are available here, and this scenario is always kept so that we would like to learn how it will behave when no data values are there. And then you are having a profile curvature. This is how it will be calculated. This is how the values exactly would be in and this is a plan curvature scenario. So, likewise using a digital elevation model on a GIS platform, we can calculate these plan curvature, profile curvature as well as total curvature. Now, there are different methods are there given by first one by the Javanbergen and Thorne, like in case of slope aspect we have discussed their methods. So, in different methods might bring some different values because the approach in different methods are different. So, in this case the profile curvature is minus 0.29. Whereas the negative value suggests that the water will accelerate as it flows over the central point in this one, and plan curvature here is going to be minus 0.36, and that negative value suggests that the water will convert as it flows over the central point. And likewise the total curvature is a positive value, but is a very small value 0.01. So, using the Javanbergen-Thorne method, when we with these input elevation values of a 3 by 3 rows and columns, this is what we get in calculations. And these again here positive in case of total curvature, positive value suggests the surface is convex at the central point. And this is how in this example all three types of curvature have been shown for the digital elevation model, which has been we have taken since beginning as an example digital elevation model, and on that model these three things have been performed using a GIS software which is called ArcGIS, ArcMap, and this is the input digital elevation model. Profile curvature is like this, plan curvature is like this, and total curvature, this is what we are seeing. For individual cells we see there. And when we go for this like ArcGIS, there is a spatial extension which can be downloaded from net from this site, and this will give us the all possible scenarios to calculate different type of curvature. Like here we can choose profile curvature, plan curvature, tangential curvature, longitudinal curvature, and based on the methods which the Javanbergen and Thorne method which we can employ there. And here also we can see how these would look in a shaded relief model. So, here is the DEM with 50% transparency over a hillside. So, hillside and DEM together, this we have seen in earlier lectures, that how these two the same data set, but one is just flat DEM having colors and another one is shaded relief model which is in black and white, but having shadows. When we overlay these two with 50% transparency, then this is what the left figure depicts. So, this is 50% transparent DEM over a hillside, and this is the same DEM over a plan curvature 20% transparency. So, now we are having a shaded relief model, plan curvature as well as DM3 altogether. One is 50% transparent, another one is 20%, and by this method we can see that where are the pronouns, valleys and ridges. So, we can very well depict where are the ridges, like here these white bright areas are depicting the ridges, and here these darker areas are depicting the valleys. So, likewise these things can be calculated. So, what are the applications? Applications of curvature map. Curvature map has been indicating for erosional studies and depositional studies and other purposes, slope stability analysis we can. So, this is what quickly we will go through, that the curvature map displays the shape or curvature of the slope, and the part of the surface can be concave, convex, and the output of curvature function can be used to describe the physical characteristics of a drainage basin in an effort to understand erosion and runoff processes, and the curvature value can be used to find soil erosion parameters as well as the distribution of water on land, because when we go for soil erosion modeling and other, there also the slope curvature can play very important role in soil erosional modeling studies, and this is how we can calculate and provide these inputs into the modeling. And the profile curvature affects the acceleration and deacceleration of flow, and therefore influences erosional and depositional process. The plan curvature influences convergent and divergent of flow. And application of these curvature maps will be useful to understand physical characteristics of a drainage basin, erosion runoff process, and in determination of local factors of dynamics of overland and inter-soil water flow. Curvatures influences soil moisture, pH, thickness of the soil horizons, organic matter, plant over distribution and cover distribution. Curvatures are an indicator of geological lineaments, ring structures, and can be used to determine fault morphology. Also in geomorphology we can employ in geological applications, and curvature can also be used to map accumulation and transit dissipation zones of the land surface. So this brings to the end of this discussion. Thank you very much.